Hi, so in this video we're going to talk about conservation of energy. Although this is a math approach, this is a part of a vector calculus class, and my goal is just to understand where the term being a conservative vector field comes from. So what is it that makes the vector field to be called conservative? And I hope that by now who's watching this knows that a conservative vector field is one whose the vector field is the gradient of a function. Okay, I'm calling the little f the potential function, and just for this work, I'm going to use the negative sign here. Yeah, so f is going to be the negative of gradient of f, and this comes from physics. Okay, so you can think of f being gravity, and the gravity is goes down, so it's a negative potential. You can think of it that way if you want to. But the negative sign is going to make us make all at the end make sense. It's not a big deal. We'd have to just define something differently if it didn't include the negative right now. So just think of that going to be the negative. So we have a curve gamma. Sorry. Have a curve gamma, goes from AB to Rn. This is going to be usually R2 or R3. Let's put an n there to like a placeholder. So gamma is a curve that starts with a point P and goes to a point Q. That's gamma. P is gamma of A, and Q is gamma of B. So we're going to assume that we have a little point, a particle, I'm saying, that goes from the point P to the point Q with an underlying vector field, right? That means that there is a bunch of arrows in the background going here. You don't have to be in any special direction. So as this little particle moves along, oh, did I grab it? I think I didn't grab it, and I can't grab it. Okay, let me grab a new one. As this particle moves along the path, it makes some, talk about the work already. I hope you recall that it's the line integral of f of gamma dot gamma prime. I'm going to calculate that in a minute. Okay, so we're going to use, that's the setup. I'm imagining that this vector field f is the negative gradient of a vector, of a scalar function, sorry, f. So f is the scalar function underneath it. And then from physics, we're going to use a couple of things. We're going to use that the force is mass times acceleration. So this is going to be an equal sign we're going to use later in a minute. That f is going to be the vector field. The acceleration is going to come from the particle moving. Now I want to talk about kinetic and potential energy. So these are two definitions again from physics. I just made a notation here to say K of P, call it the kinetic energy at a point, and the potential energy at a point. The potential energy is just the vector, sorry, the scalar function f that we're using over here. So that we're going to assume that potential, we call it in math a potential function, and it really comes from because that's the potential energy from physics. And the kinetic energy is 1/2 of the mass of the particle times the velocity, the magnitude of velocity squared. So velocity for us is a vector. So this is the velocity magnitude squared. And I put in a p here. It's going to be a little bit confusing maybe because gamma prime, right, the velocity of gamma, that's your velocity. So it's a function of t. But when I put v p, what I mean is you're evaluating the t so that you're at the point p. Okay, so hope that makes sense. So we can v of p. So this potential energy, sorry, kinetic energy at the point p means find out what t you can evaluate the velocity at that point, to be at that point. But that's the correct thing to talk about it. Okay, so we have those two things, and then from math, we're going to have to remember a couple of things. I already said that the derivative of gamma is the velocity vector. But also something we're going to use is this property of the dot product. That you find a derivative of a dot product of a function, in this case the velocity. That's the dot product. And then you take the vector functions and you take the dot product of them. Then the derivative obeys the product rule. There's going to be the derivative of of v dot the second one plus that one dot the second one, but this is the same term, so of course we can write like 1/2, like 2 times the derivative of v dot v. Right, so you can write if you want, this is acceleration dot v, but I think we're not going to need it like that. Okay. Okay, so using those two things, we're going to use this to bring this up. And we have all the ingredients, I think. We have it all. So how do we get to this conservation of energy business? So let's see. I'm going to start with what I said we had. We said that the gradient of f is the f, right? It's a potential function. I did include a negative here, so let me put the negative of the gradient as f. And we said that the f is the second law of Newton. Bring it up. So I get ma here, right? That's the a, right? Acceleration. And the acceleration is the derivative of the velocity. Right, so I just, by doing simple substitutions, start from here, and I can get to the negative gradient is m times dv dt. Very, very plain and simple. Now the next step is a little bit out of the box. I'm going to write the negative gradient of f equals m dv dt, and I'm going to do something weird here. I'm going to take the dot product of both sides with gamma prime. Right. If I knew that this was equal up to here, of course this is equal if I take dot product with gamma prime at each point. Now, why am I doing that? Well, of course you can see that on the left side this is going to be, I'm going to take the integral in a minute. But on the right side I'm going to do what I just talked about. This is the m, and this is dv dt dot v, right? So this, if we want to change the color again, this gamma prime is v, right? It's a velocity. Okay. And this is what I had over here. So dv, this is what I had right here. That see, dv dot v is 1/2 of the derivative of v dot v. Right, because I have this 2 right there. So let's put that in here. So what I end up having really, let me just go to one color now. The negative gradient of f dot gamma prime of t is 1/2 of m d dt of v dot v. Right, that's what I talked before, right? So if you did the derivative of v dot v, you will get twice this term. So I only have one of them, so it's half of that. Okay? Okay. This is a preliminary work to have it set up. We're almost there. Let's put this on the side. Let's put it over here. And let's grab this and keep working with that way. Okay. So what I'm going to do now, of course, is this is how I have this set up to do an integral. So I'm going to do, yeah, why not? I'm going to grab this. I'm going to copy. Excuse me. I'm going to move this a little bit to the right. Move this a little bit to the right, and I'm going to include right here an integral dt along the curve gamma. So this is notation I used for finding the line integral of a function dot gamma prime. So this is on the left side. This means it's, I know I'm going to use the fact that I'm integrating a gradient, so this is path independent, so this is going to be at the endpoints. Okay. So on this side, I'm assuming that you guys know that the integral along the gradient of a function is really just the function at the endpoints. It's a fundamental line theorem of line integrals, if you want to have a name for it. So on this left side, I get exactly the f function evaluated at the endpoints of gamma. And I said over here, I'm going to use the notation I had over here, that gamma of A is P and gamma of B is Q. So I'm really doing, it's going to be, f at Q minus f of P. I do have this negative here. So that's going to switch the signs, right? So let me put that negative in front of that and put it like that. So I'm using the fundamental theorem of line integrals, if you want to call it that way. Okay, some of us call it that way. Using the fact that the gradient, integrating the gradient means the work integral is path independent, so you can move, you can ignore the line integral, just evaluate the potential function at the endpoints. On the right side, well, I have 1/2, so this is a constant. The 1/2 and the m, I can put them outside, right? So let me put them like this. And if you see this, oops, I rung a little bit too much. If you see this, this is just the integral of the derivative of something. So this is just a fundamental theorem of calculus from Calc 2, and this is just the inside function, again, evaluated at the endpoints. So this is going to be, again, 1/2 of m. The inside function was just v dot v, right? Evaluated at q minus v dot v evaluated at p. So I'm going to write it like that. Now, something that I haven't used, of course, v dot v is just the magnitude of v squared. So I can write this like 1/2 of m magnitude of v. I think I was writing the notation v at q squared minus 1/2 of m v of p magnitude of that squared. So on this side, on the left side, this becomes the f of q negative plus the f of p. Correct? With I'm bringing that negative. Okay, so we have it all done. Let me now shrink this to have some space. And bring this up here. So all that's left is to move things around. You have the p's part on the left side, so I'm going to add this term and bring it over here, and it shows up like 1/2 of m of the vp squared plus f of p, so I'm bringing this one here, and then out of this term, I'm going to add it to and put it so show up on the other side, so it's f of q plus 1/2 of m of the magnitude of vq squared. Well, if you recall, 1/2 of m times vp squared is exactly what I called the kinetic energy, and f of p is what I call the potential energy. So this is the kinetic energy at p plus the potential energy at p, and this side is I have it backwards, but it doesn't matter. This is the kinetic energy at q, that's this one, and the potential energy at q. Okay, so yeah, this is what happens with a conservative vector field. We're saying that if you think what this is saying is that the energy got conserved or didn't change. If you think the total energy at the point P as the kinetic plus potential is the same as the total energy at Q, kinetic plus potential. So what we're saying is that the kinetic energy might have moved to be potential or backwards, but the total energy got unchanged, stay unchanged. And that's why the term conservative vector field comes from. It's a physics term. We use it in math, and this is the property that the name comes from physics. Okay, so I think that's a piece that's sometimes missing when we do vector calculus only. These terms are physics, originally from physics, so we have to bring that gap. So I hope that clarifies that. All right, thanks for watching.